Now, to demonstrate the first transformer equation, Vp Ip equals Vs Is, which is basically just power input equals power output, and vice versa, is quite tricky. So it did actually take a few days, and the tech helping me has a PhD in the subject area as well. We did manage to get something though. It was my idea to reverse it and put a safer input voltage in. Nonetheless, we did blow up one or two resistors and loads, but we did get a final result. So we got here the secondary output here. So the problem is alternating current. So the voltage, alternating voltage, it's quite fine, 7.5 volts, and the machine does that safely. It's in parallel. When you're in series, it creates potentially some issues because it's alternating, and the machine's Hasco the analogs work off direct, and they're not that, they don't work that well. So what we did was we put a diode. That was my tech's clever idea, and a diode only allows electricity in one direction. So we're cutting out half the current. So we're converting AC to DC, but we're losing half of it. So that the real effective current needs to be doubled. And so we've got a reading of 0.28 as the amps. So the power for the secondary is IV, so it's 0.28 times 7.5, and it gives us 2.1 watts, but it's actually double. So I've doubled that to 4.2 watts because I really should be times 2 for the amperage there. And then whenever we put a load on the primary, so we put a safe current through there too, and it is step up, so it was quite, we did have it on 6 to go to 60, and that kept on blowing stuff up. So this was as low as we could possibly get it. So we do have a voltage reading of 1.6, so it's about 2. And you can see again, we have quite a large load in there. Just to try and so they don't blow up, and so we had to do the current separately. So just being a little bit tricky on that one as well. We basically knew the voltage was 1.6, and that we measured the resistance of the coils directly as 0.3 ohms, and so that's how we got the current as 5.3 amps. And so we can use that value without having double anything, because that is the full current. So P equals IV, so that's 5.3 times 1.6, so it's 8.5. So as you can see, they don't match. One's input power is 8.5 and output is 4.2. So if you could, the heat and the sound of this gives you a good sign that there's not very good efficiency. So if I do the efficiency calculations, these are in watts, but power is energy on time, and the time is consistent. So it's the same thing as joules, the ratio. So 4.2 divided by 8.5 times 100, so it's about 50% efficient on that. And just to finish, just for completeness, the other transformer equation that you're going to have to know is one that relates the voltage to the number of coils. So Vs on Vp equals Ns on Np. So I'll just throw a question there and put the answer up there. Assuming the system is 100% efficient, what's the number of coils? And the number of coils was 80 in the primary. How many were in the secondary? So you sub those numbers in. I've got the voltages as 7.5 and 1.6 in S divided by 80. So rearrange that, retimes that, it's 375. And you know that's a step down because I've reversed it. A step up. Normally you've got this very dangerous voltage coming in from the AC. It's 240, and so it's always a step down. So I've reversed it, so it is a step up. And you can see it went from 1.6 to 7.5, so you'd also expect the number of coils to go up, which they did do, 82,375.